You don't know what Q-Fix is?
No.
You missed out.
I think it's before your
Was that before full map?
Yeah. Like, no? Yes? Maybe? Yeah.
What was that
Full
like?
map was the thing.
I don't remember. Was it the late 90s or was it the early?
I remember using it
Lot and stuff.
very early in my life.
Obviously, Run,
Dunk Life. It was amazing. Sorry, we're just living out our childhoods right now.
Yeah, my adulthood there.
Yeah, which may or may not be supported anymore because Flash doesn't exist.
Yeah.
Yeah, I remember when Pong came out. That was so awesome. That was actually pretty incredible for
Space Invaders.
74, 75.
Pac-Man, Frog,
Those are the good ones.
the original Mortal Kombat.
Oh yeah. They were only in arcades back then.
Yeah.
And then did they come
I think Mortal Kombat was like they caused like a giant like lawsuit or something over like it created the ESRB.
Oh yeah.
I feel like that would box would be like the guy, like the adult playing Street Fighter in their case. It's like this is too easy.
That was my brother-in-law. He was a Street Fighter. I played it once on his quarters, and I sucked at it. Hubert. I like Hubert. All right, so let's start out with any questions.
Too many.
Just pick one.
Oh my gosh. I don't know. Even though you went over it on like the meeting yesterday, when it came to the rest of the questions, my brain did not absorb it properly.
On
The
Master
equations of motion.
Set 5, I think I just have a question on the direction of two forces for problem 6.
Right, which one is problem 6?
The one where Gerard is pushing the cart with
Ah.
the boxes and the boats.
Okay.
I have a question on the direction of the force of friction of box 3 in relation to the cart. And then I also have a question on the direction of the normal force of the pulley and the rope. I think is okay. This one box 30 did also. I was like, where do I?
All right, so we got so it's 1, 2, 3, C. And see if I can sketch it up at least enough.
The only thing I can think of is since the cart's going this way and it's that that doesn't matter with the cart that way. Yeah. But that's what I thought. Sure.
That's what I did. Something like that.
Yeah. Perfect.
All right, and so it's being pushed this way. Did I comment on the acceleration? The cart
is to the right.
It's accelerating to the right. All right. So whatever happens, we have to have a net force in that direction. So if we're frictionless, see, this is balanced like that. Well, if this were frictionless here, then the cart would just slip out from underneath it. So the tablecloth underneath, obviously there's friction there, but think tablecloth underneath the expensive china. So since 3 is accelerating in that direction, the whole thing is accelerating in that direction, there's got to be some force pulling it that way, and that's going to be, so there'll be friction going this way on 3. And this way back on the cart. Up here, we have a tension here, so this is pulling this way, and this is pulling this way on 1 and 3. The rope is being pulled that direction. And then more importantly here, the rope is pulling this way and that way. So if this were frictionless, 2 would be shooting backwards relative to 1 and 3. So the friction would seek to oppose that, so the friction would be acting to the right here and here on 2, and then there and
Wait.
there on 3.
Could you explain that for the frictions between 1 and 2 and the frictions between 2 and 3 one more time?
Yeah, and probably good for me to think through it again. 2, 3, 1. Can I see the wording?
Yeah.
All right, so Gerard is pushing onto the cart at the downward angle. 3 boxes on it. In the past, he's had problems with excessive acceleration. Top box tipping towards him, middle box sliding toward him from his point of view. All right, so this is keeping the top box from tipping. Rope is stretched tight, not before box 1 starts tipping and box 2 starts sliding towards him. So box 2 is sliding towards him. All right. So nothing is frictionless other than between pulley and rope. Also, so the corner box 1 is not sliding on box 2. So that means that, all right, I think I might need to amend something here. Well, first off, there definitely has to be friction that way on cart 3, and then this way, box 3, and this way on the cart. I'll call it FC and FC. Because otherwise, this whole top structure would not be accelerated in that direction. I mentioned that box 2 is sliding backwards. So friction wants to oppose that. So I think we definitely would have friction here. Yeah, because if friction were in the opposite direction, then we have 2 frictions going to the right and tension going to the right. And that's, well, basically friction would be helping it move to the right. Well, it is anyway. It seems like something would want to oppose motion there. So we have the tension here. We have the tension at an angle there. Tension acting opposite that way. That way. All right, so 1 is not sliding relative to 2, so it's static friction. 2 is sliding this way. If this were frictionless, 1 would be standing still and 2 would be moving to the left relative to box 1. Therefore, friction opposes that. So this would be moving relative to the left relative to box 1. So box 1 is going to be exerting a force to the right on it. That's the way I'm seeing it here. This actually was a problem inspired by a student, because I didn't have the rope and pulley system, but I had a whole stack of stuff that was moving on the cart at the end of the class, and the student said, "Wonder how fast you could go before that thing tipped over." So I spent the next several days working through it, and then I damned him to hell, and then got back at him by making it a test problem.
Oh, can I have that sheet?
Oh, yes.
Sorry about that. Thank you.
All right, other questions?
I was wondering about number 2 on the master set 5, concerning him jumping in the air, hands back on the ground.
So I'm taking it from there. I have a couple variations of that. That's from the moment he touches. Is it from the moment he starts to leap, or where does the problem start? When landing. Okay. Until he's standing straight up again. All right. So while he's in the air, what is the normal force acting on him? None. Okay. So we're going to start out with normal force of 0. So plotting, I believe, normal force. What was the wording?
Describe exert on the ground, which is normal force, and then to the force due to gravity.
All right, his weight. So the force that he exerts on the ground is equal in magnitude to the force that the Earth is exerting on him through the normal force. So if we did that force diagram of him, we have weight acting down and we have normal force acting up. His weight is constant, close enough to count. I mean, G does vary with height, but not significantly. So we have some weight. Whatever the value of the weight is, I'm going to set that as the value. So while he's in the air, the normal force is 0. As soon as when he starts to touch, we now have a normal force. Well, you will still speed up for just a very tiny amount of time, but ultimately, as you're slowing down, I'm assuming you're going to slow down when you touch as you land. It would be very interesting to see something that is sped up when it hit the ground, but I would not want to experience it. So if he's going down and slowing down, which is bigger?
Why?
And why is the normal force bigger?
Because its acceleration is greater.
You hit a key word of acceleration, but the rest of the wording was off.
Accelerating upward.
And how do we know he's accelerating upwards?
Because he's
And I think,
pushing up.
okay, but how do we know that the upward force is bigger than the downward force again?
Because magnitude is greater.
Well, okay, then why is the magnitude greater?
Greater acceleration. But why?
There's a total acceleration. There's not an acceleration for each force. There's an acceleration for both forces combined.
Because acceleration is upward.
And we know acceleration is upward because it might have been said over here, but I'm not quite sure exactly the first word.
The acceleration is negative and the weight force is upward.
Okay,
Well, then,
maybe. Sorry, Hector.
all you think about is that the normal force is a result of him going down towards it.
I'm actually touching the ground.
So touching the ground, you get that normal force is like the result of him going. It's like the opposing force on his weight.
Ooh, be careful about that wording. It happens to oppose the weight in this problem, but don't think of normal force as opposition to weight as an automatic.
Okay, so
Yeah, well, let me sort of spoil it.
okay.
He's moving down, so his velocity is down. He's slowing down, so therefore acceleration is in the opposite direction. And since acceleration is up, this must be a bigger force than that. So, what was said earlier, I wasn't sure if you said going down or slowing down. There was some voice over here, or maybe someone else said it and I just heard it. All right, so but his velocity starts out or his normal force starts out at 0, but then as soon as he hits, well, the normal force is bigger than his weight. If the normal force were equal to his weight, he'd be in equilibrium, and his velocity won't change, which means he'll hit the Earth and then just keep going. So there's a quick spike here. So there is a brief time period in which he is still speeding up going down because the normal force hasn't exceeded his weight yet. And thus, of course, there's the traditional rip in the space-time continuum. But we will assume not the case here. And so he's going to keep going, and then at some point, do I have him, when he lands, does he go into a squat and stay there for a moment, or does he immediately pop back?
He squats and then, like it says, when landing, I still move down after touching the ground until my velocity stops, and then I am able to stand up straight.
Okay, so this part comes into, depends on how he's doing it. So if it's just a landing, and then pops back up again. So he's just only stopped very briefly. Then the acceleration is upwards until he actually stands back up. And then he's just standing normally. If he lands and then stays down for a moment and then stands up, then we'll get the double hump where he's going to squat, stay squatted for a bit, and then he stands up again. But not that far.
Are we supposed to map that out?
I think I said graph. Or did I just say what's the relationship?
Just what's the relationship?
Okay.
Could we graph it?
Yeah. I guess it's the 151 problem where I had to graph it. So, anyway. I think that answers the question. Other questions?
I don't think I went that in depth for that. I think I just used Newton's third law, and I don't think that's right.
Yeah, well, Newton's third law deals with the normal force. This normal force acting up on him corresponds with a force acting down on the ground, normal force, and this weight pulling down on him corresponds to the same amount of force pulling up on the earth.
Yeah.
So Newton's third law not quite applicable here. Other questions? Will?
With question 6 on MasterCard 6, which is the ropes and boxes on table.
Okay.
It says after you find the tension in rope 3,
Okay.
and you do the angle, okay, when you get to the point where it's nice, you're spinning mass forward.
Right.
How does that affect the tension? Because when I think about it, it's like you're spinning it as it's coming this way, but it's pulling on the rope, but as it's going this way, it's not.
All right. So if something is traveling in a circle, then there's centripetal force. If we look at the forces acting on the mass that's swinging, I think it's mass 4. We have weight acting down, and we have tension acting up at some angle. And I think I give you the angle. Or I give you the length of the rope, or what information do I give you?
You give the diameter and the time.
Okay. So if you have the diameter, the time period, you can find radius. Okay. So in the first part, when it's just sitting there and you have the rope like that, then the tension of the rope is equal to the weight. But now only the vertical component of the tension is equal to the weight. The actual tension has increased. Well, I know that component right there, because that'll be equal to the weight in magnitude. And then I've got the centripetal component here, which will be equal to mv squared over r. Or m omega squared r, whichever one you like. Yeah. So if I know the time period, I can find omega. And if I have the diameter, I can find the radius. So I could find, and I know the mass, so I can find the component, I can figure out what the centripetal force is. If I know the centripetal force and the vertical force, I can figure out what the tension is. Pythagorean theorem. Okay. So that's how it affects. So the tension in rope 4 will increase, and then that'll have repercussions. Potentially. Did that answer your question?
I think mostly.
You want to add to it?
I got to that at like 12:50 last night, and I was there, very there, and I was like, we don't know what the angle is, and we don't know what the length of the rope is. So I don't know what's going on.
All right, well, I'm going to make up some numbers then. Let's make a mass of 5 kilograms. A diameter of 3 meters and a time period of 4 seconds. So again, the facades process, do the force diagram, so I have weight acting down, I have tension acting at some angle, which I will label as theta. I'm going to set up, I know that my acceleration is towards the middle, because it's traveling in a circle. And so therefore, I'm going to set up my coordinate system. I have the J hat. Well, weight is in the negative J hat direction. I don't have to do anything with that. The tension I have to break up. So I know I have tension times, that's an adjacent side there, tension cosine theta going up, tension sine theta going to the right. Weight acting down. My equations of motion. I'll have an I hat equation and a J hat equation. My I hat equation is I have Ft sine theta, because that's the only force I have, is equal to mass times acceleration. Vertically, I have Ft cosine theta minus the weight is equal to 0. Because it's not accelerating up or down, all the acceleration is vertical. Horizontal. Substitution, I have an independent formula for weight, I have an independent formula for the centripetal acceleration. So I have Ft sine theta is equal to m omega squared r, or if you prefer b squared over r, you can do that one too. And Ft cosine theta is equal to mg. So I can judge. Ultimately, I want to figure out what the tension is. So I'm going to plug numbers in at this point. If you want to hold off on that, fine. But this would therefore be 5 kilograms. Omega is the angle 2 pi divided by how much time it took, over 4 squared, times my radius of 1.5 meters. And that is some number. .755. No, I lost one. I forgot to square it. What is that?
It's 18.5.
All right. So for my tension, I have a component going this way of 18.5 newtons. I have a component going up of 49 newtons. And I have to figure out what the sum of those two vectors is. So 18.5, 49. And then, yep. And that's my tension right there. And then you can find the angle if you wanted. I don't remember back.
Yeah.
Okay. A little bit of trick. And the mass itself does not affect the angle. It affects the tension, but not the angle.
You're
Oh,
good.
okay. So is the reason you're using like the rule of vectors where you can move like, one vector connected to the other vector to get the other side? So you did one.
Oh, as I went from here to here?
Yeah.
I know that tension is the sum of these two vectors here. And so when I add head to tail, so I just
Okay.
add to move the tail to one to the head to the other. Okay. Other questions?
I had a question about number 2, where on this master set 6.
Okay.
It's like you got these 2 boxes. It's like
Then you're pulling on the bottom box?
yeah, and then what's the maximum force that can be applied to M2 and M1 not stored? Not understood.
And I assume I gave you some values for
Yeah.
you and masses, etc.
Yeah.
All right, I'll make up some numbers. This is not the exact. It was frictionless between box 2 and the ground.
The ground is frictionless, but the coefficients between M1 and yeah, the ground is frictionless.
As with any of these problems, force diagram. I got 1, I got 2, and I got ground. All right, force diagram. What do we got? Okay, so up on the ground? Okay.
Then same thing for the second mass, right? Second mass down. And then there's no friction between 2 and the ground, but there should be friction between 1 and 2, right? It should be to the right 1, I think, and then 2 to the left.
That? Yes. Okay. That's it for friction and gravitational force.
Then we have the perpendicular forces, so that would be on. Do where I need. Is it from 2 to 1, like perpendicular to the ground?
You doing 2 and 1 or 2 in the ground? 2 and 1. All right.
Yeah. I don't know what I do.
Normal force. There's a normal force on 1 acting down on 2. And there's a normal force from 2 acting up on 1. No, because 1 is on top.
All right. So issues with the preposition. So it's up on 1.
No.
Yes.
Yeah. Yeah. And then
Normal force is a repelling force. It's trying to keep things away from each other. So it's pushing up on 1.
Yeah, and then 1 is pushing down.
Yep.
Oh.
And then with the ground is pushing up on 2.
Yeah.
Ground or 2 is pushing down on the ground.
Something like that's not my subscripts there. That 2. That's supposed to be a Y. They will not put the force high enough for me.
You also have I think the question says there's an overall force to the right.
And this is an example of other. So there's a force acting to the right of, I think I labeled it cleverly, F, capital F. That's like an external force. Pardon? That's just like an external force. Yeah. Yes. It's part of the problem. The actual source of whatever's causing that force is irrelevant. But technically, there's something over here with the force acting back on it, but we don't care about that. All right, so we no tension. We did other. We got normal. Okay. Yes.
There's a mu K value, but I don't know if that matters.
We wanted the maximum value of the F so that one does not slip.
Okay. Yeah. Yes.
Yeah. So use of K, if I gave it to you, is just there for fun.
Oh.
If it's not slipping, I know we're staying in static.
Okay.
Matter of fact, since we're at that extreme, if you're dealing with static, you have to sort of deal with extremes here. So because static friction is less than or equal to u sub s times the normal force. So since we're looking for that maximum force where it does not slip, we're at that maximum static friction. So Fs max is equal to mu s y.
So it's more than that.
So now let's do our equations of motion. We've got 4 equations of motion for 1 and 2. Oh, sorry, let's go in the order. Force diagram, direction of acceleration.
To the right.
Okay. Coordinate axes.
So like just I hat to the right and
Okay. And do we need to decompose anything?
no.
That's a nice little problem here. And then equations of motion.
So
On I1. This is the case right here where we have the same coordinate system for both masses.
take a shot at this.
Equations of motion.
Which one?
I have one.
Okay.
So I have one. You have F1.
And is that it? No.
It's
Equal to
massive
MA.
one times.
Yeah. Yeah. That massive one. Yeah, that one.
Oh.
And then for the J hat of mass 1, I have the normal force of mass 1 minus the weight of mass 1 equals to 0.
So let's take a shot at the next one.
I'm gonna say for I hat 2 that it's
F minus F1 equals MA, or M2A.
Lastly,
Normal force of mass 2 minus the normal force of mass 1
yes, but I'm going to go ahead and put in the intermediate step minus weight 2 is equal to 0, just to keep the form, but ultimately, yes. In actuality, we don't need, this formula right here is not going to do anything for us because it's frictionless between 2 and the ground. If there were friction between 2 and the ground, then Y2 suddenly has importance. All right, next step, substitution.
We have an equation for W, that's just mg.
Okay. And so that makes y1 minus m1g. Oh, let's go ahead and move it over to the other side. y1 equals m1g.
static friction is equal to the coefficient of static friction times
We have 2 normal forces here, but the normal force is the normal force at that boundary. Whatever 2 surfaces are touching, there's a normal force and friction in this particular case. So since this is the boundary we're dealing with, we want the normal force at that boundary, which is y2, or sorry, y1. I pointed to the correct one. And that is equal to m1a. And we saw f minus mu s y1 is equal to m2a. So we actually don't need to find what the normal force is unless I ask for it. Okay, the big F, what is the largest force with which we can pull the bottom mass without the top mass sliding.
Oh, okay. Oh.
And so at this point, it's plug and chug or however you wish to do it. Oh, wait a second. We do need to find y1.
Yeah, we don't know what that is.
Yeah, we don't know acceleration, we don't know y1.
Oh, but if we figure out y1, we can figure out.
And we don't know f. There's the three things.
But so if we do y1. Well, do we have masses though? We don't. I think the masses.
Yeah. So
We could find the y1.
Yep.
We have use of s, right?
Yep.
So once we have y1 use of s, and we have that first mass, we can rearrange it to get our acceleration.
Yep.
And then we'll have m s y1 and a, and if we have mass 2, we can rearrange to get just s, right?
Yep.
We have all equations.
Physics gets us this far, and now it's a math problem. If you get a negative value for big F, then you've probably done something wrong. Yeah, negative value for big F would mean either you made a mistake or box one's slipping before you do anything. I think, Zachary, you're the one who started this.
Yeah.
Does that answer your question?
Yeah.
Has it taken some of the fun out of it by not doing that much?
It puts
more fun into it because I actually know how to do it now.
You want to retain the rejoices as physics. You understand.
Yeah, like there's no rejoicing if you don't understand it. I don't know if you agree with that sentiment, but I definitely do.
I'm scared of enough problems.
That's good. Definition. What does dynamic
Equilibrium means acceleration is 0.
Okay.
Which means, relating back to that first step, which means acceleration is 0, vector acceleration is 0, velocity is constant, or the total force is 0. So vector acceleration is 0, regular acceleration is 0, instantaneous. If velocity is constant, speed and direction are both constant.
I'm sure I got that one right just off common sense. Just not. I didn't even. I forgot that equilibrium was something we even went over, and it kind of hit me on the test, and I'm like, wait. And I decided to use like if it's an equilibrium, it's not moving.
Yeah. Well, back to your original question. So equilibrium has, those are the qualifications for equilibrium. There's no comment about its movement. So static equilibrium is at rest relative to the reference frame. And dynamic equilibrium, it's moving. So right now, from my point of view, this table is at rest. It's staying at rest. Flat Earth is in equilibrium. If I move towards it, it's still in equilibrium. By moving doesn't change the nature of what's happening to it. So dynamic equilibrium, it's moving relative to your reference frame. So if I'm the reference frame, then yeah, my moving doesn't do anything to it. I feel like there's a follow-up question.
It is moving. The table is moving.
Yes.
Then that situation, you would be static towards you.
In the case, all right, so movement, the velocity of an object is always relative to something. One exception, speed of light. Speed of light is always the same, regardless of the reference frame. So If it's at rest relative to me, I would say it's in static equilibrium. Badly worded. If it's in equilibrium and at rest, I would say it's in static equilibrium. If I'm moving at it at a constant speed or constant velocity, it's in dynamic equilibrium relative to me. Okay. But it's still equilibrium. The total, my moving does not affect the forces acting on it.
Are you in static equilibrium relative to yourself?
Not necessarily equilibrium. I'm static relative to myself. If I'm moving at a constant velocity towards the table, then yes, I would be in static equilibrium relative to myself.
Which is the reason that it's in dynamic equilibrium. That's weird.
Yeah, and there's some other weird things that at the end of 252, when we get to special relativity, there's some really mind-blowing stuff around that. And a hint to those who will remember it, this discussion here leads nicely into the solution to the twin paradox. So just sort of tuck that away till you, at the end of 252.
So when you're like, because I know how to get all my values now. So I remember you did something yesterday where you like added stuff together from those, like those values you have over there.
If I added these together, then the friction would disappear.
Yeah.
But I still have two unknowns. So that was originally where I was going, then realized, wait a second, we have three unknowns.
Okay. So it just be.
If I know my acceleration already, I can just add these two together and not worry about this term.
Okay.
Not necessarily the simplest way in this problem.
And is G just like 9.8 in this problem? Like,
Yeah, probably.
Yeah.
Yeah, if I don't specify or imply, it's most likely Earth.
Okay.
Yep. No, I have not forgotten. All right. Any other questions right now? All right. I do want to talk about test corrections. The rules of test corrections. One, corrections on separate paper.
Okay.
Don't do the corrections on the original test, please.
Yeah.
I think it's in one of the videos, the student who did the original test in red ink, did all his corrections on the original test in red ink. And so I'm supposed to try to figure out what he did the first time instead of the second time. He did not get benefit of that. Big thing, you are trying to convince me. That you understand. The ideal I'm shooting for here is this is a second chance to, or another chance to learn the material, and so you're trying to demonstrate that you understand how to do it. So usually not a big issue or 251, but just throwing this out there. If I see two with actually identical answers written down the exact same way,
Just like they didn't change a single thing. Like they came to like the same thing.
or they worked together, or one of them did it and the other one copied it, or something like that. That's copying, working with other people, I don't have a problem with. There's nothing inherently wrong with that. Copying someone else's answer with their work, that, as you should know, is forbidden. So you're not going to convince me that you understand if I see two identical answers. I'm not going to play the game of which person I think wrote the original and which person copied it. Yeah. Just providing an answer does nothing. Again, usually not an issue for 251. 110, it's a real issue. No matter how many times I say it, some people will still just write an answer down. Those are the big things. Those are the two big ones right there. way it's going to work is it's sort of a scaled system. So if you get an A on this, you can bring it up to an A plus. If you failed it, you can bring it up to a C.
What if I got a C plus?
And then if you've got a C on it, then, I mean, basically, I've set the linear relationship there. And so that's halfway between there. So this would end up being a 3.15. And then it scales from there.
Okay, so theoretically, let's say that I got a 2.3.
Set up a graph here. Original versus best final. And so we have so 0 maps to 2.
Yeah.
And 4 maps to 4.3. You got a line there. Find the equation of the line. You can find the slope. Intercept right there.
Yeah.
And then plug in your value, and you get out the best you can get.
Okay. That's not too bad.
So if you missed say 60 points, and that got you a C, just for example. You do your test corrections. You convince me that you understand 2/3 of what you did. So in other words, you got 40 out of the possible 60. Well, you could have boosted, since you got a C, you could have brought it up to a 3.15. So you could have boosted your grade 1.15. So basically, I take that fraction times what you could have gotten, and then add that to your original grade, and that's what the final grade is. I don't round it there. For the first time around, it's, you know, your grade will end at either a 0, a 3, or a 7. As in 2.3 for a C plus, 2.7 for a B minus, so forth. After I do this, I don't round this off. So you might end up with a 3.54. Well, not in this case, but if you end up with a 3.54, I don't say, oh, that's an A minus 3.7. It goes in the grade book as a 3.54. 3.54 actually is an A minus, but it's not the default. Got an A minus, you get a 3.7.
So, from my prior experience with test corrections, do we have to like always show that we understand what we miss, or do we have to show that we understand everything?
What you missed.
Okay.
I mean, you're not going to get credit back for things where you didn't miss anything.
Yeah.
So you don't have to redo the entire test, just the problems you've missed.
Okay. And we're explaining, right? Like the math is not going to be enough. Like if we showed you
No.
all the math.
I read the math. So unless you get into really esoteric math, you're probably doing the problem wrong. But
So work out the problem, and then you see the math, and then I give you like 2 or 3 sentences.
yeah. And I will say, no one's asked it yet, but I'll go ahead and throw this in there about, do you have to explain why you put down your original answer? And no, you don't have to explain why you put down your original answer. However, I have noticed from my grading point of view that people who do that, I tend to be more convinced that they understand.
I mean, for me, it'd be like, all you get out of me is I literally just blank.
And, okay, that probably wouldn't help a whole lot.
Yeah, that's usually why I like leave something blank. It's just like my brain is just like, I don't know.
All right, so once you've started the lab, once we've started rejoicing in the other room, then I'll hand these back. If you're in the middle of doing a trial, please don't just stop in the middle of a trial to look to see what you got. The test is not going to go anywhere.
When do these test corrections do?
Typically 2 weeks.
Like from when you get them?
Yeah, from when I hand it back. But that puts us during Thanksgiving, so we'll just say 3 weeks this time.
That's so good. You're like,
You're
you're a real one, honestly.
I don't want, now, let's say in 3 weeks, it's still not ready. Just let me know. And tell me when I'm going to see it. The 3 weeks is not a hard and fast deadline. The main thing, I don't want you waiting until the last week of school to do this. I've gotten the whole stack of, hey, here's everything I haven't done for the entire semester. And It's usually a load of crap. And so I want to avoid that. It's hard to be, the students who do hand in the huge thing, I'm thinking, well, I probably should have studied for that last test more than working on that stuff.
Yeah. I'm glad you're doing this, because I missed some things on that test where I'm like, I think about it afterwards, I'm like, how did I miss that? Like, I don't know. Yeah.
So this is your chance to relive the love and the rejoicing. All right, let's head over to the other room and stop this and figure out where all the